Tuesday, we had a review of the Friedman, Lemaitre, Robertson, Walker metric and the Friedman equation, so the Einstein equations applied to this metric. We also saw, and this was the meat of the course, we saw when and how recombination and decoupling happen. And since then, photons mainly free stream toward us, and these photons at microwave frequencies are the cosmic microwave background. So this lecture will be based on starting to talk about the cosmic microwave background, the physics of the cosmic microwave background, and I will start telling you, if we have time, about how we can use the cosmic microwave background in order to understand, to infer the different cosmological parameters. Or in other words, how the different cosmological parameters impact the CMB power spectrum, okay? But before, let me tell you a little bit of the history of how this ancient light was discovered, okay? So this light was discovered by accident. In the year 1964, two astronomers working at Bell Labs in New Jersey, Arno Penzias, who unfortunately passed away, and Bob Wilson, who is a researcher at the Center for Astrophysics at Harvard, were experimenting with a horn antenna built to detect radio waves. To measure these faint radio waves, they had to eliminate the interference from their receiver. And they did that by cooling liquid helium minus 220 Celsius, so only 3 degrees Kelvin above absolute zero. Now, when Penzias and Wilson reduced their data and found a low, steady, mysterious noise that persisted in their detector, they started to become a little bit, they started to work hard to eliminate this noise. And I used to believe this was a myth, but actually I've heard Bob Wilson telling this story, so I feel confident to tell you this story. The actual story is that they were trying so hard to get rid of the noise that they climbed the detector, cleaning it, thinking that perhaps that noise was because of droppings of pigeons in the detector. Of course, they didn't get rid of this noise. At the same time, and not far from them, in Princeton, also New Jersey, Dickey and Peebles, who is now a fantastic professor at Princeton University, and Wilkinson were preparing to search for the microwave radiation that they knew should be there because as a consequence of the hot Big Bang. So a friend of both, Berkey, a professor of physics at MIT, told Penzias about a preprint that he had seen by Jim Peebles on the possibility of finding this cosmic microwave background radiation left over from the Big Bang. And then Penzias and Wilson began to realize that actually it was not droppings of pigeons what they have detected, but it was actually the cosmic microwave background. And they won the Nobel Prize for this. So of course they couldn't have won it was an accident that it was the cosmic microwave background, but of course they were amazing experimentalists who did such a good measurement that they reached the level of the cosmic microwave background. Not an easy task to achieve. So after the cosmic microwave background, I will tell you a little bit of the history that I started telling you 2 days ago, and then we will go over the math that describes this, okay? But let me tell you that after the cosmic microwave background temperature of about 2.7 Kelvin was detected, different satellites were launched in order to study the fluctuations around this temperature that we call the monopole, okay? So the first of these satellites, known as COBE, the Cosmic Background Explorer, which operated from 1989 to 1993, found that the CMB actually has fluctuations in 1 part in 100,000, okay? This part of the sky may have a little bit more temperature than 2.7 Kelvin, okay? 2.7 Kelvin times 1 plus 10 to the minus 5. This other part of the sky may have a little bit less than 2.7 Kelvin, and so on. So this is a map of what they have seen, okay? The red band, so the different colors correspond to different temperature fluctuations, different temperatures, yes? The red band is our own galaxy that is masked here because it's so bright that we need to mask it when we do the CMB analysis in order to take out the very bright part that is coming from our own galaxy. Okay, so different, and for this, by the way, they also won the Nobel Prize. So different satellites were launched after COBE. The second satellite to be launched to space, as I told you on Tuesday, was WMAP, that operated from 2001 to 2010. There were several papers in which they constrained very precisely the cosmological parameters. And the last one to be launched, the last one of these satellites, was Planck. It was launched in 2009, and it operated until 2013. There is still a last paper in progress, and I actually was told that it's probably going to be submitted in the next day or two to the archive. So this is the last paper, I believe, with Planck results that will release the last likelihood of Planck that people like me then can use in order to test their theories or extract information in other ways that perhaps the Planck collaboration didn't think about. All right, so cosmologists like me then analyze this data from different collaborations that made the data publicly available, not only from satellites, but also from telescopes all over the world. Okay, there are several of these telescopes nearby in Chile, in the Atacama Desert. There are other telescopes, for example, in the South Pole, okay? And what we do is we analyze the statistical properties of the temperature fluctuations at different positions in the sky, and from there, we infer the physics of the very early universe. We test inflationary scenarios, like Mehrdad explained you, and other scenarios. And we also try to get information, and we do, actually, from the composition of the universe at large scales, okay? We know how much dark matter we have, how much dark energy we have, etc. And we extract a lot of information from the cosmic microwave background. Good. So let's get started talking a little bit in more detail about the CMB, okay? So let me start here, thank you. So the CMB monopole, okay, and by this I mean the average temperature that was detected by first time by Arno Penzias and Bob Wilson, was measured to be, let me write this number, 2.725 plus minus 0.001 Kelvin, okay? Now, let me briefly review, perhaps you saw it before with Raul, I'm not sure, but let me briefly review the theory, the basics Blackbody physics, okay? We know that the CMB is at very high precision, behaves like a Blackbody spectrum, okay? So let me briefly review the theory, the basics of Blackbody physics. Blackbody. So the energy of a black body, so let me say, what is a black body? it's an idealized object that absorbs all the electromagnetic waves that, that falls on it, okay? However, a black body also emits, and emits at a temperature that depends on the frequency. So the energy of a black body at frequency nu, say, can be written in the following way. This is the energy density, actually, of a black body. This can be written as 8 pi h bar over c cubed. I'm being good with the c's here. Let's see how long I last. Over e to the h bar nu over kt minus 1, okay? At low frequencies, we have the classical regime, the Rayleigh-Jeans regime. And at higher frequencies, we have an ultraviolet catastrophe, okay? We have infinite energy density of radiation. So this is predicted classically. So quantum mechanics comes to save us and gives an exponential suppression of h bar much larger than kt. So the peak of the black body spectrum is at energy, the peak of the black body spectrum is at energy h bar times nu peak, yes, which is approximately 2.8 K times temperature, okay? The CMB is about 2.7 Kelvin, as I just told you, and this means that the peak is about 2 millimeters, okay? So lambda peak is about 2 millimeters. Now, you can compute the energy density from there, okay? Integrating over frequency, you can compute the energy density of a black body. And this gives us the following. If we compute the energy density, what we get is that the energy density is some constant times T to the 4, okay? Where alpha is a radiation constant and is closely related to the Stefan-Boltzmann constant. Okay, so once we have the numerical value for alpha, actually I can write it down. Alpha is 7.5 times 10 to the minus 16 joules per meter cube per Kelvin to the 4, okay? We can derive the CMB number density. And this is getting interesting now. We can know how many photons we expect to see from the CMB in a centimeter cube, for example, okay? So the number density of CMB photons is equal to, putting the numbers, 4.11 times 10 to the 8 meters to the minus 3. So we have 411 CMB photons per centimeter cube. Okay, already we have a number. This is getting interesting. Yes? We have photons that are approximately a temperature of 2.7 Kelvin, and we approximately have 411, 410 photons per centimeter cube.
Can I ask something?
Yes?
When you observe how many of these photons we can actually observe, because we observe a tiny fraction of the actual Blackbody spectrum.
Yes. But we observe photons all over the sky, right?
Yes, but we observe with specific frequency, I think.
Yes. So how many? The number density is an average number density, okay? And then I will tell you at which frequencies we observe. But this Blackbody spectrum is a general statement. So the CMB is essentially very good approximation a black body with temperature of 2.7 Kelvin. And as we will see, the blackbodiness, I'm inventing a word here, I think, of the CMB has been detected with great precision, I think I told you this, by COBE, okay? In particular, by this instrument called FIRAS. Yes, I mentioned it, that it put limits on the spectral distortions, okay? So the blackbodiness of the CMB has been very accurately measured by COBE FIRAS, and since then, we didn't have any other limits on, for example, the spectral distortions coming from the CMB. Now, let me show you, because I'm telling you that this has been measured with great precision, and I thought I would show you a plot of this blackbody spectrum. So let me show you here and show. Let me show you this. Okay? Here we can see the intensity as a function of frequency, where, and you can see the error bars. Notice that the error bars, in order for you to see them, have been blown up by a factor of 400, okay? So when I say that COBE FIRAS measured this very precisely, I really mean it. Look at this plot. This is a very almost perfect blackbody spectrum. And so FIRAS measure the blackbodiness at wavelengths of between 0.1 millimeters to 10 millimeters, okay? Now, not only that, we learned that we have, okay, what did we learn so far? That the CMB temperature is 2.7 Kelvin, that the CMB behaves as an almost perfect blackbody spectrum. Now let's move on. We talked about the monopole. Now let's move on. And the next moment to pay attention to is the dipole, okay? So let's talk about the CMB dipole. So in the late 1970s, another milestone was achieved. Researchers detected a dipole of the CMB. And a dipole, as you know, what is a dipole? What do I mean by the dipole of the CMB? You can think about the dipole as temperatures in opposite directions of the sky separated by 180 degrees, okay? So here we will have a hot spot, and here we will have a cold spot, for example, okay? We can think about the temperature in the opposite direction is colder by the same amount relative to the mean, okay? Or hotter. So the dipole was measured to be 1,000 times the value, less than the value of the monopole. So delta T dipole was measured to be approximately 10 to the minus 3 times the temperature of the CMB, okay? And this CMB dipole is actually not primordial. The dipole is due to our motion through the CMB rest frame. And there are many motions that I'm considering here, okay? This is the sum of individual motions. For example, the motion of the Earth around the sun around the galaxy, and so on, okay? So we can determine the velocity with respect to the CMB rest frame from the measured dipole. And we learn that this velocity is about 370 kilometers per second, okay? This dipole is not primordial. So in general, when you see the peaks of the CMB, you will see them starting from the quadrupole, which is primordial, okay? And it's the first primordial multiple moment that we can observe in the CMB. Now, let's talk about the CMB anisotropies. Yes? That is not intrinsic dipole. Well, there is an intrinsic dipole, right? There is an intrinsic dipole, but it's buried under this dipole, which is different motions, the motion of the Earth around the sun, and so on. Yes. Because it's buried, we start with the quadrupole. Okay, so good. So let's talk about CMB anisotropies in general. And this is when it starts getting fun. CMB anisotropies. Okay. So I already told you that COBE was the first satellite that measured the CMB temperature fluctuations. And one of the COBE's instruments was FIRAS, as we already mentioned, okay? COBE instruments, there was FIRAS. There was another one called DIRB, Diffuse Infrared Background Experiment, okay, which did the same as COBE, but at shorter wavelengths, okay? So DIRB is another instrument. The third one, called DMR, Differential Microwave Radiometer, actually measured the temperature differences across the sky, yes? And this one is the one that gave us the measurements that we will be studying in more detail today. So DMR's measurements actually led to the Nobel Prize in 2006 by George Smoot and John Mather. And they measured the temperature fluctuations across the sky. And in particular, they found that the quadrupole they measured the quadrupole, which is the largest primordial fluctuation of the CMB. Now, the interpretation of these fluctuations, as you saw from Mehrdad, or as you heard from Mehrdad, is that these fluctuations have been laid out by something like inflation, okay? Perhaps it was not inflation, but it was laid out in the very early universe by some period like inflation, or inflation. Okay, so what did we learn with DMR? We learned that delta T over T, this value actually, is about 10 to the minus 5, okay? And now let's describe this delta T over T. And in general, what we do in cosmology is to take the temperature fluctuations and make a spherical harmonic decomposition, okay? This is like a Fourier transform, but in 2D. Remember that I told you that we can think about the surface of last scattering or about the moment of decoupling as a surface where the photons scattered for the last time, yes? So we will be thinking about a sphere around us, and we will be decomposing the temperature fluctuations over this sphere, okay? And a Fourier transform over the sphere is like making a spherical harmonic decomposition, yes? Good, and this is what we will start doing. So CMB fluctuations, let's start doing this. We will have delta T over T, that depends on angles, and we will start from the quadrupole, okay, until some L max. This is a spherical harmonic decomposition where m's goes from minus L to L, just like in quantum mechanics. And we will have the spherical harmonic coefficients and the spherical harmonic themselves that will depend on angle, okay? Notice that there are 2L plus 1 m's for each L, okay? So if I take L equal 2, I will have 5 m's and so on, yes? The largest L's will be, the smallest L's will be the largest scales in the sky, okay, the largest angles in the sky. And as I go up in L, I will move down in angular resolution, Yes? Okay, so in general, you can think about the mapping from angle to L and vice versa as theta is roughly equal to pi over L, okay? So for example, L equal 1 correspond to the dipole, theta equal pi, L equal 2 correspond to the quadrupole, pi over 2, and so on, yes? Smaller L's, larger angles, larger L's, smaller angles. Good. So from here, we can derive ALMs, okay? We just have to integrate over delta T over T with the YLM conjugate, okay? So we can write down, using the orthogonality of the spherical harmonic coefficient, the spherical harmonics, we can write down ALM as the integral of delta T over T, double integral. Well, let me write it this way. The integral of delta T over T, that will depend on theta and phi, YLM conjugate, that depends on theta and phi, and the solid angle over here. Yes? And one condition of the ALMs, notice that the ALMs, these coefficients, okay, can be complex numbers. Yes? And they will satisfy the following relation. So ALM conjugated will be equal to -1 to the m AL minus m. Okay, this is a relation that, that you may find useful in order to do calculations later on. Okay, so inflation can lay out the initial conditions for these temperature fluctuations and for the perturbations of all the species in the universe, okay? In particular, we are talking about the photon density fluctuations, which are related to the temperature, as we saw last class. Now, the coefficients, in general, if we don't have non-Gaussianities from the early universe, as you saw today with Merdad, and if you don't consider non-Gaussianities coming from late time evolution, we think about the ALMs as Gaussian distributions, okay, as having Gaussian distributions with mean 0 and some variance that we will call CL, okay? Now, we will prove a bit, in a little bit, that these CLs, if there are no anisotropies in the universe, will be independent of M. Good. So, and we will start talking about the power spectrum, okay? The power spectrum, basically, is given by the two-point function of these ALMs, yes? And the power spectrum has been predicted and measured with great accuracy over the past many decades. Here is the temperature power spectrum of the CMB as a function of multiple moment or angular scale in the sky. You see that we start with 90 degrees and we continue. Okay, so from this temperature power spectrum, just to keep up the motivation, we will be able to learn about the physics from the very early universe. For example, we can measure, and this has been measured, the scalar tilt. You have seen with Merdad that this is predicted to be almost scale, the power spectrum is predicted to be almost scale invariant, but not exactly scale invariant. So we can measure NS, which is the scalar tilt. We can measure the amplitude of scalar perturbations. And we can also measure the different cosmological parameters that affect this power spectrum in different ways. Okay, they affect the power spectrum in different ways. And I will be showing you in a little bit how the different cosmological parameters have an effect on the power spectrum. Now, let's write down the power spectrum, okay? So the two-point function of ALM A, L prime, M prime conjugated, okay, is equal to CL, the power spectrum, times delta LL prime, delta M, M prime. I'm assuming statistical isotropy, okay? This is assuming statistical isotropy. This has been put to test, and this has passed the test pretty well. There are some claims of breaking statistical isotropy, but in general, the universe turns out to be pretty isotropic, assuming statistical isotropy. Now, CLs, remember, the CLs are the variance of the ALNs. Now we are ready to calculate the variance of the CLs. And the variance of the CLs is known as cosmic variance, okay? So it's an intrinsic variance that we will have no matter what, no matter the noise of our instrument, we will have an intrinsic variance because we can measure these CLs once in the sky, okay? We have one universe. We cannot rerun the universe many times. Okay, so cosmic variance. Let's go on and calculate the variance of the CLs, okay? How do we calculate the variance of the CLs? The variance of the CLs, well, the variance is nothing else than CL, CL prime minus CL, CL prime. Yes? Let's write this down explicitly. So this is equal to 1 over 2L plus 1, 1 over 2L prime plus 1, the sum over M, ALM, let me see, this is the bracket here, ALM conjugated, the sum over M prime, A, L prime, M prime, A, L prime, M prime conjugated, minus CL, CL prime. Okay, I'm writing CLs here also. This is another way as 1 over 2L plus 1, the sum over M of ALM, ALM conjugated. Okay, this is what I'm doing here. Okay, good. If we massage this, and we can go over the details, but I will leave you this for homework, okay? If we massage this, we get the following answer. So I leave you this as an exercise. It's very easy, really, it's like 3 lines to show that this is equal to 2 over 2L plus 1 CL squared delta L, L prime. Okay? So we learn here what is the variance of the CLs. So the variance of the CLs, we learn that is equal, sorry, this was the variance squared. So the variance of the CL is equal to 2 over 2L plus 1, the square root of this CL, okay? So this is one part of the error bars in the CL. And take a look at this. We are seeing that the lower L's, okay, the largest angular scales in the sky, have larger error bars. And we can see there. Do you see? These are, so in green, the shaded green, that's the cosmic variance, okay, of the power spectrum, without considering detector noise. You can see already that the error bar, the cosmic variance error bar, is larger at larger scales, and it's smaller at smaller scales, okay? And this is because smaller scales have higher values of L. Now this is interesting I think perhaps you saw it with Merdad or not, I'm not sure, but inflation, the superhorizon modes at recombination affect the lower L part of the power spectrum. So it's interesting to study that part because we may gain intuition, we may gain insight of what is happening in the very early universe. However, we have the unfortunate fact that we live in one universe with cosmic variance, okay, and the cosmic variance becomes larger exactly in the region of interest, okay? So this is a fact. We have to deal with it. Some of you, I think, mentioned that they were studying, I think Katerina is your name? Yes, you mentioned, I remember, you mentioned that you were studying the suppression at large scales, and you mentioned it to be between 2 and 3 sigma. And with temperature measurements, you just cannot do anything about it. Even if you measure it better and better, you're not going away from that 2 to 3 sigma. That's why it's interesting, for example, to look at polarization as a prediction of these models that may give rise to this kind of suppression or not. Or perhaps you see that they disagree and it's a fluke. Yes? I'm referring to the shaded green region. Yes. Good. So let me continue. The actual error bar from the experiment is not only cosmic variance, but it's actually also instrumental noise, okay? I'm not going to give you here a fit for instrumental noise because it depends on the experiment, but let me just write the instrumental noise as NL. Here, this will be instrumental noise. Sorry to make you turn on and off the light. Instrumental noise, okay? So the total error budget in the CLs will be given by 2 over 2L plus 1. Sometimes we measure in a fraction of the sky, okay? Not the entire sky. Sometimes we have telescopes, or even if we have satellites, we have to mask different parts. For example, we mask our own galaxy and we mask point sources that are very bright, okay? So the smaller the fraction of the sky that we measure, what do you expect the error to be? Larger, okay? So naturally, the fraction of the sky goes in the denominator over here, and then we will have the cosmic variance contribution plus the instrumental noise, okay? And in general, the cosmic variance contribution will affect the large scales more. This is because of what you saw just here. And the instrumental noise, because of the beam, for example, will affect the smaller scales or the larger L's. Yes? Good. So this will be, yeah, this basically goes under the name of shot noise, and this is cosmic variance. Okay, so now that we started talking about the power spectrum, I want to make contact with your lectures on inflation that you have learned from Merdad, yes? So why do I say that measuring the CMB can give us a hint, or we can learn also of what is happening in the early universe? Well, let me write down here. We can relate the temperature fluctuations to the curvature perturbations, as we saw from Merdad's lecture, at horizon crossing, okay? This is something that you saw. And they're related via something that we know as the transfer function. Okay, let me write down this. So I will write down, this part will be connecting observations to the early universe. Okay, so schematically, we can write something like this. The temperature fluctuations at some time eta, okay, and at some scale k, will be related to the curvature perturbation at horizon crossing, and for some scale k, yes, times a transfer function for these temperature fluctuations that come from solving the Boltzmann equations, okay? So this is a stochastic variable. Of course, it may have, we don't know what this variable is. It's not that we can go and measure the curvature perturbation. What we measure is the statistics of this variable, okay? And you actually learn how to calculate the power spectrum of the curvature perturbation, okay? So we will be able to relate the power spectrum of the temperature fluctuations with the power spectrum of the curvature perturbations, okay? So let me actually write down the following. I will write down the temperature power spectrum. And because next class I will be talking about polarization, let me already start by defining the temperature power spectrum as CLTT over here, okay? This corresponds to the temperature power spectrum, okay? So we can write the temperature power spectrum as 2 over pi, this is the definition, the integral of k squared dk, the power spectrum of the curvature fluctuations, and the transfer function of the photons, okay? So this part over here is given by early universe physics, okay? You give me a model of inflation, I solve for the background equations, I solve for the Mukhanov-Sasaki equations of motion of the inflaton field, for example, and I can compute the initial curvature power spectrum. So this is related to early universe physics. Early universe physics. And this is related to late universe, late time evolution, okay? This part, the transfer function, comes from solving the Boltzmann equations for the evolution of the photons in our universe, where you need to take into account the evolution of all the species in our universe, not only the photons. They're coupled to the baryons. Remember that they are coupled at the time of recombination. They're coupled. It's all a fluid to the dark matter, to neutrinos, etc. Okay? So this is related to late time, the late time evolution of the universe, and this is coming from observations. Before I go on, let me mention something here in passing, that this is a non-invertible problem. You may be tempted to say, okay, you give me the observations, I know the transfer function, I can tell you exactly what the curvature perturbation looks like. And actually, I worked very hard on my PhD to try to put constraints on the power spectrum, okay? Put error bars on the power spectrum and on possible inflationary models that could give rise to that power spectrum. Yes? What is non-invertible is that if you have the CLs, you cannot tell, this is the inflationary scenario that governs our universe. That is a non-invertible problem, okay? But you can put constraints on the shape of such a potential that could exist in the early universe. Just wanted to mention this since it's closely, it has a special position in my heart. Yes? Well, so what I'm saying that is non-invertible is you can start from the CMB observations and put constraints, okay, on the power spectrum. That's fine. What is non-invertible is that different inflationary models may give you the same observable. Yes? Okay. You had a question? Okay. I thought you raised your hand. You can have questions also. Okay. So what is this transfer function? Good. So since we have a few classes only, I'm not going to solve the Boltzmann equation here, but I want to give you a feeling of what happens when we solve the Boltzmann equations, okay? So let me talk about this transfer function. So this transfer function basically can be written in the following way. The transfer function for the photons, okay, can be written as an integral from 0 to today, d eta, and this corresponds to the source, delta t, k, eta, and this part over here, I will call it P, corresponds to projection effects, okay? K, eta naught minus eta right here. Okay. Now, what I'm showing you here, and this depends on K, is that this can factorize into a physical source, okay, that will come from solving the Boltzmann equations, and geometric effects from the fact that we are actually observing everything in projection in our sky. Okay? Now, so I will call these sources and this projection. So, okay. So this transfer function in general, for example, there are codes that solve the Boltzmann equation, and you can extract the transfer function from publicly available codes, okay? So for example, codes such as CAM, you can download it very easily, or class, okay? CAM is written in Fortran, class is not. But you can compute the transfer function from these publicly available codes, okay, that do it in a very fast way. In something like 5 seconds, you can actually compute the power spectrum of the CMB, yeah, with lots of tricks that have been developed over the years. And you can compute this transfer function. Now, let's take a look at some simple examples for this transfer function, okay? So that you start building some intuition. Time? Yes. Okay. So what happens at large scales, okay? You saw already what do I call large scales? I will be referring here to modes that were outside the horizon during recombination. What is the scale that corresponds to modes that were crossing the horizon at the time of recombination? And I know you saw this because you saw this in order to understand one of the problems that led to the theory of inflation, the horizon problem. What is that scale? Sorry? What is the scale in the sky if you look at the CMB? About 1 or 2 degrees. Yes. Good. So when I say large scales here, I will be considering scales that were outside the horizon at the time of recombination. So scales larger than about 1 to 2 degrees. Okay? So what happens at large scales? Large scales. Whoops. So the large CMB scales actually have not been, it's nice to start with them to give you some intuition because they have not been affected by sub-horizon physics. So the only thing that actually happens to them is projection effects, okay? This part, they have not been affected yet by sub-horizon physics. So the large-scale CMB spectrum is simply the geometric projection of the primordial power spectrum from recombination to us today. And in the Sach-Wolf regime, okay, I will call it this the Sach-Wolf regime, Sach-Wolf regime, the transfer function is simply given, is proportional to a Bessel function that just comes from projection over the sky, okay? So in this regime, we can write down the transfer function of the photons as 1/3 times the Bessel function, yes, spherical Bessel function, with the following argument, k eta naught minus the time of recombination. So this is the distance between today and recombination, okay? Okay, so then we know the transfer function, good. So then we can write down the CMB temperature power spectrum. We just learned how to do it. Let's write down the CMB temperature power spectrum. We just need to take the integral over the square of the transfer function and the primordial curvature power spectrum. So the CMB temperature power spectrum is equal to here 2/9 pi, the integral of, well, let me write dk here, k squared, the power spectrum of the initial curvature perturbations, times the Bessel function squared, and the argument is k times the distance between recombination to us, okay? Good. Now, there is a nice property of the Bessel functions, and is that they peak when the argument is equal to L, okay? These are very oscillatory functions. If you want, you can take a look in Mathematica, or you can look at Wikipedia to see the form of these Bessel functions, and you will see that these are oscillatory functions that peak when the argument is equal to L, okay? So they are peaked. This is something that you will use over and over again in cosmology, okay? They are peaked at k eta naught minus eta recombination being approximately L. Good. So then we can, assuming that this is a smooth function, we can evaluate this function at the peak roughly to get a rough estimate of the Bessel function, yes? And this is the following. CLTT will be proportional to k cubed times the power spectrum, the initial curvature power spectrum of k, evaluated at k equal to L over eta naught minus eta recombination, times an integral of d log x j L square x. Okay? Yes, I just multiply and divide by k, so we have d log x, okay, making a change of variables. And this integral over here is proportional to L times L plus 1 to the minus 1. Yes? So here we learn something. Let's write down this. We can write down L times L plus 1, CLTT, and this will be proportional to k cubed, the initial curvature power spectrum of k. Sometimes you will see this quantity as the adimensional power spectrum, so you may have seen it with Merdad as written like this. Okay? Good. So this means if this is roughly scale invariant, this means that we should expect to see roughly a plateau okay, if we plot this quantity, L times L plus 1 times CL, we should expect to see roughly a plateau at large scales. Look at that. Well, I'm not showing you what is plotted, but here, this is the reason why we plot L times L plus 1 times CL, okay? Because at large scales, we expect to see a plateau. We actually, do you see this plateau here at large scales? We actually don't quite see a plateau. We see a little bit of a deviation from the plateau, and this is because of something known as the integrated Sachs-Wolf effect, okay? The gravitational potential actually has evolution because of dark energy, okay? So the derivative over time of the gravitational potential is non-zero, yes? So this changes it a little bit. Do you see that it goes slightly up? This is because of something known as the integrated Sachs-Wolf effect, but you can see already, we already understand the superhorizon, the large scales, the superhorizon component of this power spectrum. Good. So let's now talk about the modes that were inside the horizon during recombination. Yes? And these are the interesting ones. Well, all of them are interesting, but there is a lot of physics in the modes inside the horizon during recombination. Now, because the density perturbations were produced all at once, at the very beginning of the universe, the phases of the sound waves were synchronized. And this is a smoking gun for inflation, okay? The fact that we see the peaks and they are not produced over and over again means that so if they were produced over and over again, they would be washed out. We see the peaks, so there was some clock, some synchronization of these density perturbations. Perhaps it's not inflation or something else, but definitely they look synchronized, okay? Now, the energy density of the photons, let me start understanding or trying to understand the shape of these acoustic oscillations, okay? Why do we see these peaks? And I will start with a zeroth order understanding of these, and then we will add complexities, okay? But let's look at the simplest scenario. So we saw already that the CMB is a very good approximation, almost a perfect black body, okay? And this means, again, as we showed at the beginning of the class, that the density perturbations of the photons of the CMB is proportional to the temperature to the 4, okay? The temperature of the photons to the 4. Now, if we take delta rho over rho here, delta rho over rho gamma, yes? This will be related to delta T over T CMB, yes? So this will be delta T gamma over T gamma, yes? With a factor of 4 here, okay? So in particular, let me define this variable. I will be working with delta T over T a lot, so because I'm lazy and I don't want to write delta T over T all the time, I will define this variable theta, okay, which is also common in the literature. In particular, and we will see probably next class, but perhaps we can start seeing this class, we will see how this theta, for now believe me, and then we will prove it, obeys the following equation, which is a wave equation at 0th order. Okay? So theta obeys the following equation, the partial derivative with respect to time of theta plus the sound speed, yes, the velocity of the sound wave squared times Laplacian of theta. This is equal to 0, okay? This is the sound speed of the photon baryon fluid, okay? And this sound speed squared is defined as delta P over delta rho, and this is equal to 1/3, okay? Since this fluid is photon dominated, yes? So the sound speed will not be the speed of the photons in vacuum, but it will be the speed of the photons in vacuum over square root 3, okay? Because the photons are propagating in a plasma. Okay, so if we have this wave equation, of course, we can write down a possible solution for this wave equation. Let's do it. A possible solution for this wave equation is given by the following. Theta of kt is equal to initial condition of theta, cosine of ks, and I will define s in a moment, but this is the distance the sound can travel until the time of recombination, plus delta theta, delta t, at time equals 0, sine of ks over kcs, okay? And s is just the distance from the beginning until the time, until some time, okay? At recombination, it will be recombination, but in general, it's until some time cs dt prime, okay? Okay. This equation, let me just emphasize, this is a simplified version of reality. Just at 0th order, when I first show you the CMB acoustic peaks, I wanted to start with the simplest possible solution, okay? This is a simplified version. Then there are other effects that come in. But let's look at this simplified version. So, and also to first approximation, it works quite well. Okay, the CMB power spectrum. Where are the CMB peaks located? We could start by asking that. So we know, let's look at this, the time derivative of the temperature fluctuations, okay, is related, because of the continuity equation that you already saw, is related to minus 1/3 k times V gamma, okay? This is the continuity equation. Now, if we assume negligible velocity perturbations at the very beginning, which it's okay to assume, okay? Give me 1 second. We can write down the following solution. Theta at t equals 0, cosine of ks. Yes?
I think in the paper question there is a sign.
Oh, yes. Thank you, thank you. Thank you. Good. Okay. So, since, as I told you, photons decouple from the rest of the fluid at the time of recombination, and what we see is these photons mainly free streaming towards us today, so we see a snapshot of that time, we should evaluate this at the time of recombination, okay? We want to know what was happening at recombination. So, yes? Yes. It's a good assumption based on observations. Oh, which assumption? I just assumed that the velocity perturbations at the beginning were negligible. Yeah. Okay. So if I evaluate this at recombination, what we get for S is the distance the sound travel from the beginning until the time of recombination. And where are the peaks located? Well, obviously the peaks, we can write Kp is K peak, okay? P times pi over S star, where S star is the distance the sound travel until the time of recombination, okay? And this P is 1 for the first peak, 2, 3, etc. Obviously, don't get confused with this notation. I know you will not, but let me just be pedantic and mention this. K is a continuous function, okay? Obviously, this is not quantized. It's just that I'm referring to the peaks here. We want to know where are the peaks located. Okay. So P equal 1 is the first acoustic peak, P equal 2 is the second acoustic peak, and so on. And so let's, okay. So we will see, so already we see from here that these peaks are harmonically separated. And roughly this is what we see, okay? We see the first acoustic peak roughly at 200, the second roughly at 400, and so on, okay? You know, then we see a damping. Of course, this is at 0th order. This works well. Then, of course, we have photon diffusion that produces this damping, and we have other effects, the Doppler effect, relativistic effect, and so on, that we are not considering here. But to first approximation, we can understand where are the peaks located. So let's try now, and I think you did this in a different way, but let's try now to understand where is the first acoustic peak located. Let me just mention the following. Perhaps you're confused because this cosine has positive values and negative values, and here you're observing all peaks, okay? This is because we are taking the temperature fluctuations squared, okay? This is the solution of the cosine squared. So the first acoustic peak corresponds to what we call compression modes, modes that were going into the potential well. The second acoustic peak is actually a trough, but you see it as a peak because I'm plotting the angular power spectrum. This is known as rarefication modes, okay? These are modes that were having the counteracting effect of the pressure from the photons, and so on. The third one is a compression mode, the fourth one is a rarefication mode, and so on, okay? Good. So why am I talking about K's and angles? Perhaps this is confusing, okay? So let's take a look. So what we are seeing is that the temperature fluctuations, okay, depend on wave number, on wavelength, okay? And we see this wavelength projected in some angle in the sky, yes? So, for example, a wavelength lambda will be projected roughly at an angle alpha in the sky, and this will be given by lambda over the distance from the Big Bang to today minus the distance from the Big Bang to recombination. So the distance from us to recombination, okay? This is us. This is the surface of last scattering. So we see a wavelength projected in the sky, okay? And we are trying to understand what's the angle subtended by it. Yes? Now, D0 minus D recombination is roughly 14,000 megaparsecs, okay? So this number is roughly 14,000 megaparsecs. Good. So what is the angular position in the sky of the first acoustic peak? Let's derive this. Well, we are almost there. We have the first acoustic peak. We can write it K1, okay? We can write it as pi over the distance the sound traveled until the time from the Big Bang to the time of recombination, okay? Now, what is a star? I told you what CS was, okay? So CS is C over square root 3. Yes? So we can write down here this will be equal to square root 3 pi over the distance to recombination. Sorry. No. Sorry. What I meant to say here is that, yeah, this is the distance to recombination, okay, which is a longer distance. And here, I will make the following approximation. So alpha 1 will be given by d recombination over d today. And here I'm making the following approximation, that d today minus d recombination is approximately d today. Yes? So it's a ratio of distances. The distance from the Big Bang to recombination and the distance from the Big Bang to today. So if we put numbers here, okay, if we consider a flat universe and we consider that recombination happened at redshift of 1100, then we can solve for this, and what we get is that this happened between 1 and 2 degrees in the sky. Okay, you can do this by considering that distances in a flat universe grow as 1 over 1 plus z to the 1/2 for the relevant times. Okay, so the first peak, again, that we observe is evidence of the fundamental wave, okay? It's a compression mode, and then we will have rarefication modes, and so on. So let me start talking now about the physics and how we can use the CMB to measure the different cosmological parameters. Good, this is what we just saw. Okay, so here is, in words, what I just told you, but summarized, okay? Again, let me tell you that gravity tries to compress the fluid in potential wells, the potential wells created by the dark matter. The photon pressure will be a counteracting force, and these counteracting forces will result in acoustic oscillations, okay? There will be a sound wave that is propagating in the early universe. Now, we saw that at 0th order, this is equivalent to a harmonic oscillator, basically. You can think about a mass on a spring falling under the action of gravity. And I like this analogy. I teach at Harvard, I teach both cosmology for graduate students, and I have been teaching waves phenomena for undergraduate students. So at the end of the lectures, I always, you know, after we saw the harmonic oscillator and we saw many examples in nature in which we can think about different physical phenomena as behaving like harmonic oscillators, I end up with the early universe. And we can understand at 0th order, by just understanding the solution of a simple harmonic oscillator, how the early universe works. Of course, this is at 0th order. I'm not adding complexities yet. Okay, so potential wells appear in regions of density enhancement, okay? And compressed regions are hotter, and rarefied regions will be colder, okay? Compressed regions will be more density, will be hotter, and the opposite. So we see these oscillations as sort of frozen at the time of recombination. And modes, there were different modes. The perturbations happen at different wave numbers, but modes that were caught in an extrema appear as peaks and troughs in the temperature fluctuations, but at peaks in the power spectrum. And again, as we saw, the wave numbers are harmonically related to each other. Now, what happens with, how can we use the information that we learned from the CMB power spectrum to understand the composition of the universe? Okay, we know the physics, so let's think together. What happens when we have more or less variance, for example? Okay, so what will happen is that variance will low down the baryon photon oscillations, okay? So if we have more variance, the compression will get enhanced over the rarifications, okay? More baryons trying to go into the potential wealth. And the amplitude of the odd peaks will get enhanced over the even peaks. The odd peaks are the ones that correspond to compression modes. So more baryons will enhance the compression modes, which are the odd peaks, okay? What else? What happens if we enhance the amount of dark matter in the universe? Well, if we enhance the dark matter in the universe, this will reduce the overall amplitude of the peaks, okay? Because the oscillations will have less amplitude because there will be less radiation ejecting pressure on the photon baryon fluid. There is a damping tail also that we haven't understood yet. We are seeing it, but we haven't understood. Oh, I'm pointing here, but you saw that there were peaks and then there were damped, okay? And the damping tail, as I mentioned, are due to photon random walk, okay? Photon diffusion actually is causing this damping tail, also known as the silk damping. And the position of the peaks, as I will show you in a few seconds or a few minutes, will depend on the curvature of the universe. I think at some point in the discussion the day before yesterday, we were thinking of what happens if we have more or less dark energy in the universe, and we were talking about having different positions, okay? The position of the peaks will displace to the left or to the right. So we will see how the curvature of the universe, as well as the dark energy, for example, will affect the distances, okay? And this will affect the position of the peaks, as we see from here, okay? The positions of the peak are ratios of distances. So having more or less dark energy and more or less curvature will affect the position of the peaks. So let me show you in the next 3 slides what happens with the main components of the universe and what's their effect in the CMB power spectrum. Of course, so let me first say that I will show you the effect of the different components of the universe on the power spectrum, but these components are degenerate, okay? We came up with a way of representing the power spectrum that is not optimal in the sense of, it's optimal in the sense that we understand the physics of the different species in the universe. But it's not optimal in the sense that they are degenerate. These effects are degenerate with each other. So we will see different effects, but of course, you can never go and just look at one of them and measure whatever component you're interested in, okay? You have to look at the combination of these different effects to measure the components of the universe. Okay, so again, let's look at the different components. We learned that in the universe there is approximately 5% of the energy budget is in baryonic or ordinary matter. Approximately 27% is in cold dark matter, and 68% approximately or 70 is in dark energy, okay? Okay. I like these slides also because they take me back to my time when I was a student. My PhD advisor was Wayne Hu, and he made these slides. So here we see the effect of the variance on the CMB power spectrum, okay? So you can look at this pink or whatever color that is bar. When it's going up, we are increasing the variance. When it's going down, we are decreasing the variance. Look at when it's going up. The odd peaks are enhanced over the even peaks. Do you see the first peak? In the third peak, it's quite obvious that these peaks are enhancing over the even ones. And this is, again, what we just explained. The compression modes are getting enhanced. Now let's take a look at what happens when we add dark matter. As the dark matter increases, the overall amplitude of the peaks decreases, okay? And we can see, we can understand that. We already understood this. We are changing the photon component, okay, which is causing this effect in which when we add dark matter, we see less amplitude of the acoustic peaks. What happens now when we add spatial curvature or dark energy, okay? So let's take a look actually at the curvature, which has the most pronounced effect, okay? So let's take a look. When the pink bar goes up, we are increasing the curvature. When it goes down, we are decreasing the curvature. The yellow power spectrum is moving to the right and to the left. Do you see? Why is that? Because we are changing the distances. So the wave numbers, or the wavelengths actually, are projected into different scales, angular scales in the sky. And the position of the peaks, the position is in L, for example, is related to the angular position in the sky, okay? Okay, so I think I have 5 minutes left, and I will leave you these minutes for questions to me. So with this, I will end the class today. And next class, what we will do tomorrow, I'm having 2 lectures. Tomorrow, we will see in more detail what happens with the CMB temperature. This was CMB temperature 101, 0th order, but we will see more phenomena that happen actually that affect the CMB temperature power spectrum, and then we will go into the polarization, and I will show you how measuring the different modes of the polarization, in particular measuring the B modes of the polarization, we can, by measuring the B modes of polarization, we can learn about the energy scale of inflation. And this will be very related to the primordial physics lectures that Mehrdad has been giving to you. Thank you. Questions?
Questions, anyone? Can you just repeat again why increasing dark matter dampens the whole height of the peaks?
Yeah, I knew this question was going to come. Well, actually, okay, let's go here. Sorry. Yes, so that's what I told you. So basically, there will be, when I enhance the dark matter, I will have less radiation producing pressure, okay? Because I enhance the dark matter, but I also want to keep the matter radiation equality time the same, okay? So I will have less radiation producing pressure, so it's less the counteracting force that you have, so more.
So you're adding dark matter and reducing photons.
Reduces the power spectrum, yes. So more dark matter, less radiation, yes.
So when you show the plot increasing the curvature, it appears that you have an extra peak. There's a peak appearing for large scales, small l.
Ah, yes. Here, yes, I know what you're talking about.
So why is that?
Yes. So let's look at the dark energy, for example, okay? Well, here is sort of a peak, let's look at the dark energy. So the dark energy is actually the effect of seeing the plateau get enhanced over large scales is exactly what I was telling you about the integrated Sach-Wolf effect, okay? This third over here is related to the gravitational potential over 3. When there is dark energy in the universe, there is a time derivative of this gravitational potential that is non-zero, which produces this integrated Sach-Wolf effect. For the curvature, the distances, at large scales, they get very distorted. So that's why, it's reaching unobservable values of the curvature, but they get very distorted. So you see the spectrum having this enhancement at large scales.
In the small scales, I see that the curvature is shifted a lot in the scale range, in the L range.
It shifts what, sorry?
It shifts in the L range.
Yes.
The yellow one.
Yes.
What's the reason for that?
Well,
with respect to the dark energy.
Yes, because the curvature will have more of an effect at smaller scales with respect to dark energy. Remember that dark energy, so those modes at small scale re-enter the horizon earlier on, okay? So they are affected by curvature by a larger amount of time. Dark energy is only relevant at times close to today. Yeah, so that's why. That's a great question.
Questions? So if not, let's thank Cora again.
Thank you.
So have a coffee break and then we'll come back for the